Now that we've seen how we can solve a fairly typical simple equation, even though we have a ways to go with all the situations that can arise, we do have an overview of how to solve a simple equation, and we have an idea of what solutions might mean and what form they might take. Let's consider a couple of examples of systems that might actually occur, and systems that are easy to understand. Okay, so here we have a two-tank system, very much similar to the mixing situations that we saw in previous chapters, but now we have two tanks each with its own inputs and outputs, and also with exchange between the two tanks. R1 is the rate at which solution is being pumped into the first tank, R2 the rate at which solution is being pumped into the second, R3 mixed solution from the first tank to the second, R4 mixed solution from the second tank to the first, R5 and R6 the rates at which solution is being pumped out of the two tanks. Now there are some constraints on these rates. For example, R5 plus R6 had better be equal to R1 plus R2, or these tanks, assuming implicitly that they're originally full, aren't going to be able to hold the solution. They're not going to be able. They're either going to have to expand, and let's assume they can't do that, or they're going to burst if these two aren't equal, or they're going to implode. And that could be written very simply as R1 plus R2 equals R5 plus R6. Similarly, tank 1 has to have the same input as it has output. So R5, whatever comes out, is going to have to equal whatever goes in, R1 plus R4, which comes in from here, minus R3, which goes out here. And of course, we could have written that R5 plus R3 equals R1 plus R4. The net in equals the net. The net in, these two, equals the net out, these two, and so forth. We could write a similar equation for tank 2, and in more complex situations we might have a number of additional constraints on these rates. We would also have concentrations C1 and C2, concentration C1 going in at rate R1, concentration C2 at rate R2. We'll let V1 stand for the volume of tank 1, V2 for the volume of tank 2, and the concentration in tank 1 will be Q1 of T over V1, Q2 of concentration tank 2, Q2 of T over V2, where Q1 and Q2 are the amounts of the solute and in the two tanks and so forth. I'm not going to write that out. So the question now is, what's our differential equation, or what are our differential equations for Q1 and Q2? Well, on the first level, Q1 prime of T equals rate of solute in minus rate of solute out. And let's just look at Q1 prime of T and see what that would be. At what rate is solute coming in? Well, that's going to be R1C1. At what rate? Now let me back up. There's also solute coming in here. So that rate is going to be R4, the rate at which solution is being pumped in, times the concentration of solute in tank 2, and that concentration is going to be Q2 over V2. And then that's going to be minus the rate at which solute exits. Well, it's going to be exiting at rate R5 and R3. Both of these exit rates will be mixed solution at concentration Q1 over V1. So that's going to be R5 plus R3 times Q1 over V1. Similarly, Q2 prime of T be the rate at which solute is coming into tank 2 minus the rate at which solute is going out. The rate at which solute is coming in is R2C2, and it's also coming in at rate R3 times Q1 over V1. And that's minus the rate at which solute is leaving. Well, it's leaving at the same rate it's going in from this tank to the first tank. That's going to be R4 times Q2 over V2. And I was going to put both of these in parentheses, but we'll just put another minus sign here. Minus R6 times Q2 over V2. So that could be simplified a little bit. This equation, or this system of equations, then can be written in this form. Now there is another little twist in these equations. We do have equations much like the ones we solved previously. This would be a homogeneous system where we just have Q1s, Q2s, and Q1s. Every term is either a derivative of Q1 or Q2 or a Q1 or Q2 term, and they're all linear. But now we have this non-homogeneous part, which we did not see previously. And of course, this means that later on we're going to have to develop means to solve non-homogeneous equations. In any case, this is one example of a situation in which we might well end up, or we might well be able to model the situation with a system of two equations. And you can imagine that there could be additional tanks, so we could have systems of as many equations with as many variables as we might wish. Of course, we probably wish that the system is as simple as possible, and that might be completely valid from both an engineering and a mathematical perspective.